Welcome to Industrial PLC Applications. This video is on off-delay timers, TOFs, and is a part of the Deeper Look series. The off-delay timer frustrates a lot of experienced programmers because it doesn't work right, or at least it doesn't work the way they think it should. Just like its cousin, the TON or on-delay timer, it looks for a change in state, otherwise known as COS, at its input, the .in. However, it looks for a different change of state. A TON looks for a false to true transition at the .in, from 0 to a 1. That's when it begins its timing cycle. A TOF looks for a true to false transition to trigger its timing cycle or function. To better understand a TOF's operation, let's watch a second-by-second operation of a TOF instruction. When the logic is running and the TOF logic is not called upon, we have the shelf state of the timer. It can be seen that the only contacts or members of the timer construct that are true in this shelf state is the not Q, or the Q not being energized, and the programmed time, which is set and static. The output, shown on the top as a pilot light, is off, and the push button, shown along the bottom, has not been pressed. Therefore, none of the active inputs or outputs are energized. In order for the TOF to do its job, it needs two transitions to complete its task. First, it needs to see the .in go true. This sets up an internal latch in the timer instruction, which is shown by the .fetch, waiting for another change of state to trigger the timing. So the instant the push button is pressed, the .in is made true, the .fetch is latched, and the output Q changes state and goes true. This causes the normally closed not Q to open. Naturally then, it results in the instantaneous energizing of the pilot light output, and it will remain on. When the push button is released, a falling edge or true to false transition occurs. This transition is detected by the .fetch, which starts the timing function to increase the elapsed time. Eventually, the elapsed time is going to reach the same value as the programmed time. When this happens, most of the internal variables will change state. When the elapsed time equals the program time, the Q is turned off and the not Q is turned on. This of course means the light must turn off. At the same instant, the .fetch is released, ready to be latched again on the next false to true transition, detected at the .in. So getting back to our frustrated programmers, what they want is a duration timer, something that will let an operation work for a set amount of time and then shut down. Because this instruction requires two changes of state at the in to start timing, it's not suitable for a duration application. Well, in order to use the timer to use its output while the timing is taking place, the .in has to be turned on and off again quickly, and then it should work. But in order to create a duration style timer, there are two easy choices available. The first choice, and it seems to be a natural one, is a timed pulse timer, and it can provide a simple solution. Just keep in mind, it may not have the desired effect. Once the .in is satisfied, the timer turns on its Q and leaves it on until the ET is equal to the PT, until the elapsed time is equal to the program time. That sounds like a good idea, and that sounds pretty much what we want, right? Sometimes things come with a catch, and the time pulse looks like an easy solution, which it is, but it has a catch. Notice on our timing chart that once triggered, the Q will stay on only for the duration of the program time. And even if the .in remains true, once the time's up, it turns off. Conversely, once started, it will fulfill its timed duration, even if the .in is dropped. It is not de-energized until ET equals PT. The other solution is to use a ton or on-delay timer and take advantage of its internal bits. Whenever a ton is started, its .reg bit is set to true to indicate its .in is true and its timing. However, its Q bit remains false until ET equals PT. This allows you to use the not Q. The not Q will become false the moment the timer is finished timing, because ET now equals PT, and the .Q becomes true. So during the time that you are timing, and the Q is not set, a task can be performed. So if you want a running process to shut down after a period, or if you want to program some recovery time to avoid complete shutdowns for brief interruptions, then a TOF is a great selection. It's just not well suited for time duration applications. This has been another video in the Deeper Look series. Thanks for watching.